typically we want to find the output of a DTLTI system, and we are given that LTI system are described by the convolution equation x convolved with h. And well, if we have h, then we can write this equation, of course, and in time and in frequency or in z domain, we know that the convolution equation becomes multiplication in the z domain. Now, how is this compared to the previous equation? In the previous equation, we saw that discrete time LTI system are written in this form. This in the constant coefficient DTI system, discrete time system. In this form, we have the relationship of the output as some relationship of the input and its path, as well as its path output. In here, we're writing it as a convolution equation. Notice that they would result in the same output when we begin with the relaxed condition. So if this system is relaxed, that means all initial values are 0 and we start to pump into x, then we also can write the same output as convolving x with the impulse response. Remember that the impulse response is always computed in the relaxed condition situation. Let's try to find out what is h of n. We know that h of n is h of z in the frequency domain, and therefore h of z is simply yz over x of z. So now the question is how to find h of z. And to do that, we're going to begin with the difference equation and perform the ZTransform. Let's see how. On the right hand side, you can see that this is the original difference equation we have, which is relating the y's with the x. We're going to take the ZTransform both sides. And what you remember is that the ZTransform of yn is yz. ZTransform of yn minus 1 is z minus 1 yz. And ZTransform of yn minus 2 is z minus 2 yz. Similarly, for ZTransform of xn is xz, and ZTransform of x of n minus k is simply z minus k xz. So once we know how that we are going to use this property of the ZTransform of the time delay property, then you will realize that this step is quite trivial. So again, remember that the ZTransform is linear. We can break out this into this equation over here and then apply this principle. I should say this property. So we have this step now where we are now in the z domain of the difference equation. We bring the yz out and the xz out as well, and we are going to figure out that h of z equals to yz over x of z is simply the coefficients, the constant coefficients, times the power of z associated with the index at its negative power, divided by the same coefficients multiplied by z at the negative power. So this is the polynomial associated with the coefficients of the x divided by the polynomial of the coefficients associated with the y. Remember that the b's are associated with the x and the a's are associated with the y's. Now, since we have already found what is h of z, then finding h of n is trivial. Inverse z transform, it will give you h of n. Once we have found h of n, then we can again go back to this equation to find y of n using convolution equation. But remember, we have already shown many times that multiplication is a much easier task than convolution. So if we have found h of z here, then what we are going to do is we are going to multiply by the z transform of x of n, which is x of z, to get y of z. Once we have y of z, then the idea is simple. To get back into time, we do inverse z transform to get yn. So in these 2 pages, we have seen how to reconcile h of the convolution equation, x of n convolving with h of n to get y of n, as well as starting from the constant coefficient difference equation to get h of z. In the next page, we'll give you some examples. Thank you.